So now we will go to module 4, LTI system properties in terms of impulse response. According to syllabus, it is module 3. I have covered module 5, Z transform. Okay, so according to my completion of syllabus, I have completed 3 modules. Okay, then I am now moving to module 4. So I have named it as module 4, LTI system properties in terms of impulse response. Here you have studied LTI system properties as linearity, causality, okay, memoryless. Then you have studied stability. Okay, now we are going to study the same properties but with respect to impulse response. Okay, you have seen impulse response where during your convolution sum and convolution integral. Okay, where you have been given with h of t or h of n. Okay, you got the response of the system y of n or y of t. Okay, so now we are trying to learn the properties of systems with respect to systems with properties of systems with respect to impulse response. The first one is systems with or without memory. Okay, so a discrete time LTI system is said to be memoryless if and only if its impulse response is of the form h of n is equal to c into del of n, where c is a constant. Okay, so what they are telling is, okay, you can call a system, LTI system, as memoryless, okay, when the impulse response is expressed in terms of h of n equal to c del of n. Okay, so proof of this, consider LTI system with impulse response h of n. Input is x of n and output is y of n. Okay, so according to your convolution sum, what do you write? X of n convolution with h of n, right? So x of n convolution with, what is h of n? H of n is c into del of n, c into del of n. Okay, which is c. X of n convolution with del of n is x of n itself. Okay, we have shown this. You can put summation, this equation into summation k equal to minus infinity to plus infinity. Okay, that equation x of k del of n minus k. Okay, so this is, okay, telling that this equation y of n equal to c into x of n. When I give this equation to you and ask you whether it is a memoryless or memory, then you will straightforward tell that it is memoryless. Why? Because the nth value of output y of n is depending only on nth value of the input x of n, and hence the system is memoryless according to your previous, okay, concept. This is memoryless, and now by considering h of n equal to c into del of n, again we are proving that it is memoryless. Means when your impulse response is of the form c into del of n, then, okay, the LTI system is memoryless. And for continuous time system, it holds good for continuous time system. Okay, it still holds good. H of t is equal to c into del of t. So basically your h of t or h of n should be consisting of del of n terms. Either it is a shifted version or anything, but it should consist of del of n version. So if h of n or h of t is consisting of del of t or del of n terms in that equation, then you have to consider it as a memoryless. Okay, second property, causality. Okay, a LTI discrete time system is causal, okay, if and only if its impulse response, okay, if and only if its impulse response h of n is 0 for n less than 0. So the condition is that h of n is equal to 0 for n less than 0. Okay, that is, a causal sequence h of n automatically implies a causal system. What is this telling is h of n equal to 0 for n less than 0 means left sided values, they are 0. Okay, h of n is 0 for n less than 0 means n equal to -1, -2 and so on till minus infinity, they are 0. Means such a sequence is right sided sequence, and as I told previously, right sided sequence is also called as causal sequence. Okay, left sided sequence which is from -1 to minus infinity, it is anti-causal. Okay, when we are dealing with the causality Z transform, I explained this. Okay, so now we'll go for proving it. Again, considering this LTI system, x of n, okay, output is y of n, and with impulse response h of n. So what it is? It is y of n is equal to x of n convolution with h of n, which is equal to summation k equal to minus infinity to plus infinity x of k h of n minus k. Okay, now according to the equation, what it is telling, h of n is equal to 0 for n less than 0. H of n is equal to 0 for n less than 0, which implies the shifted version of h of n minus k is equal to 0 for n minus k less than 0. Right? If h of n is equal to 0 for n less than 0, it is obvious that h of n minus k is equal to 0 for n minus k less than 0. So h of n minus k is 0 for n minus k less than 0 or n less than k, or can I write it as, okay, or k greater than n, right? For k greater than n, h of n minus k is 0. Your equation can also be now written as, okay, y of n. Okay, so what you are telling is h of n minus k, this value is 0 for k greater than n. Means from minus infinity to plus infinity, can I write it as minus infinity to n only? Why? Because this k value is tending from minus infinity to plus infinity. But according to this equation, h of n minus k is 0 for k greater than n. So anything after n is equal to 0. So why to calculate that? So basically you can write it as k equal to minus infinity to n. Okay, x of k. Okay, x of k h of n minus k. Okay, so from the above equation, okay, it is clear that the output y of n at time n is a weighted sum of the values of the input x of k for k less than or equal to n. So now you can see that, okay, y of n is depending on only the values of, this is at n, okay, y of n is at n. If you calculate this, also k is equal to at n, right? And what are the values after that, before that? Minus infinity to n. Means according to your causality previously, y of n, the output of the system should depend only on the present or past values of the input. So present value means at n, y of n at n, and past value means minus infinity. So it is depending on both past and present, and hence the system is causal. Either it can depend on present or past or combination of both. And according to this equation, it is indicating the same, and hence, okay, and hence this condition h of n is equal to 0 for n less than 0 holds good for causality. For continuous time systems also, continuous time system, okay, to be causal, a system to be causal, h of t should be equal to 0. You go to the third property, stability. Okay, a LTI system is bounded input, bounded output, stable if and only if its impulse response h of n is absolutely summable. Okay, you have the condition that summation k equal to minus infinity to plus infinity, magnitude of h of k is less than infinity for bounded input, bounded output, stability. Okay, so for the system to be stable, the impulse response h of n is absolutely summable in the sense it is finite, which is less than infinity means some finite value, 10, 15,000, 10,000, anything which is countable, okay, which is absolutely summable. So again, considering a LTI system with input x of n, output y of n and impulse response h of n, okay, we write that y of n equal to x of n convolution with, I have drawn the diagram only once, okay. When you are asked with the properties, explain the stability property with respect to impulse response, then draw the LTI system and then you can write this summation k equal to minus infinity to plus infinity x of k h of n minus k, okay. Now taking magnitudes on both the sides, on both sides of equation, okay, what it is magnitude of y of n is equal to magnitude of y of n is equal to magnitude of summation k equal to minus infinity to plus infinity x of k h of n minus k, okay. Now there is one mathematical, okay, property which we call it as triangular inequality, okay. Using triangular inequality, what it tells is the sum of the magnitudes. Sum of the magnitude means this is, okay, magnitude, okay, there is sum of the magnitudes, okay, is greater than or equal to the magnitude of the sum, okay, sum of the magnitudes, okay. So when you go on summing them, okay, so when you go on summing them, you get sum of the magnitudes for each value of k and so on, okay. It is greater than or equal to the magnitude of the sum, okay. So that tells that, okay, magnitude of y of n, okay, is less than or equal to summation k equal to minus infinity to plus infinity magnitude of x of k, okay, magnitude of x of k and h of n minus k. Is it fine? So now using the commutative property of, okay, using the commutative property of convolution, you can write it as h of k x of n minus k, because x of n convolution with h of n is equal to h of n convolution with x of n, okay. And hence now, okay, what I have done is using triangular inequality property, it was y of n was equal to this, but it tells that the sum of the magnitudes, okay, is greater than, this is greater than or equal to the magnitude of the sums, okay. And hence I can write like this. Now the same thing, the RHS can also be written as less than or equal to summation k equal to minus infinity to plus infinity, okay, magnitude of the product, magnitude of the product is product of the magnitudes, and hence I can separate them, okay. Now since you know that when you define the stability, you usually write it as x of n is bounded. Since x of n, you tell that it is bounded, because for bounded input itself you can provide a bounded output, and hence I am bounding a input, okay. And okay, also you can shift the sequence and there is bound does not change even if you shift the sequence. Now what you have done is x of n minus k is less than or equal to m. So can I use that into my equation? Magnitude of y of n is less than or equal to summation k equal to minus infinity to plus infinity, magnitude of h of k, and what is this? M. X of n minus k is less than or equal to m. I have written m. So now this is finite. Okay, for the system to be stable, only this should be finite. Okay, therefore summation k equal to minus infinity to plus infinity, magnitude of h of k. Okay, therefore magnitude of this is should be finite. Should be finite for y of n to be finite. Okay, this is how the stability property for a system with respect to impulse response is. Okay, for continuous time system, okay, integration minus infinity to plus infinity, h of tau magnitude d tau is less than infinity, the condition for stability. Okay, we'll go for the next one. Okay, invertibility. Basically, invertibility is for a system that is always exists a inverse of the system. Okay, so for a system to be invertible, okay, there should be inverse of the system. Okay, means you should be able to retrieve. Okay, you should be able to retrieve your input from the output. Y of n you get from x of n, y of n equal to x of n. You should be able, when it is an inverse system, you should get x of n from y of n. That is invertibility. Okay, so here invertibility is defined as, okay, it is a system is said to be invertible if and only if, okay, h of n convolution with h of n inverse gives you del of n. Okay, so now I will try to draw the system. X of n is given to a system with impulse response h of n, which produces, as you know, y of n, which now I will write it as y1 of n. As I told, inverse of the system is when y of n is given to a system, it should give me x of n. Okay, where I will write now here, this x of n is nothing but y of n. Okay, so what is y1 of n? Y1 of n is, okay, y1 of n is, okay, this one, h of n convolution with x of n, or x of n convolution this. And what is y of n? Y of n is, okay, x of n is input, convolution with x of n convolution with h inverse of n. Okay, sorry, this is inverse, h inverse of n, x of n. Okay, y of n is y1 of n, y1 of n convolution with h inverse of n. And what is y1 of n? X of n convolution with h of n convolution with h inverse of n. Okay, now the condition is h convolution, h of n convolution with h inverse of n is del of n, right, according to the system given thing. So that is del of n. And as you know that, okay, x of n convolution with del of n is x of n itself. Okay, means now, okay, we have recovered the input from the output. Okay, so for a system to be invertible with respect to impulse response, okay, convolution of h of n and its inverse should produce you del of n. For continuous time systems, okay, h of t convolution with h inverse of t is del of t. So this is the invertibility property.